In this video, we're going to go through everything you pretty much need to know about the threshold frequency and the work function. So I've written two model definitions here, but we're going to go into what these actually mean. So let's first talk about what's happening in the photoelectric effect. So we have electrons on the surface of a metal. We have some sort of light source, and photons are what carry light. These photons have a specific energy associated with them. When the photon hits the electron absorbs the energy from the photon, and if it gains enough energy from the photon, then the electron is able to escape the surface. The work function is the minimum energy that's needed for the electron from the photon so that when it absorbs the energy of the photon, it can escape the surface. And it's dependent on the threshold frequency. So the reason for that is because the energy of a photon is equal to Planck's constant multiplied by frequency. We're replacing this energy with work function, which is represented by this sign here. And that's equal to Planck's constant multiplied by the minimum frequency that's needed for the electron to be emitted, essentially, because the energy is proportional to the frequency. This h here is constant. Now, this minimum frequency is what we call the threshold frequency. So it says the minimum frequency that's needed for the electron to escape the surface of an atom. It's very important that you include the surface of an atom, because if we think about outer shells, the work function is the energy for like this electron to be emitted and not this electron, because this electron needs to gain extra energy before it can even be emitted to excite, but excitation is a whole other topic. Okay, so now that we've established where this equation comes from, let's rearrange it. We want the threshold frequency, which is equal to the work function divided by Planck's constant. Now, work function, because it's a type of energy, we always have to use it in joules in calculation. Right now we have it in electron volts. We can use the fact that 1 electron volt is the elementary charge. So it's 1.6 times 10 to the power of minus 19 joules. So to go from electron volts to joules, you're basically multiplying by 1.6 times 10 to the minus 19. So if you take 4.3 and multiply onto it, 1.6 times 10 to the power of minus 19, that will act as your work function. You can then divide that by Planck's constant, which is given to you in an exam. And what that will give you is the value of 1 multiplied by 10 to the power of 15 hertz. So that's what the work function is and how you use it. What about if the the photon doesn't have enough frequency to match this frequency? What if it has a frequency of, let's say, 3 times 10 to the 14 hertz? In that case, the energy of the photon would be less than the work function. Remember, energy is proportional to frequency. So if the energy is less than the work function, then the electron will just absorb the energy, but then it'll release the energy. It won't escape the surface because it doesn't have enough energy to escape the surface. But what about if the photon has a frequency that's larger than 1 times 10 to the 15? What if it's something like 1 times 10 to the 16? In that case, it has more than enough energy to escape the surface. But then what happens to that extra energy? Because now it has too much energy. It has more energy than the work function. So we write here, energy is more than the work function. And that's what this second calculation focuses on. What we say is, if we draw this out again, if we have an incoming photon, if the photon energy E is larger than the work function, because the frequency is larger than the threshold frequency, then not only is the electron escaped from the surface, but the difference in energy becomes the kinetic energy of the electron as it escapes. That brings us to the equation that the photon energy, hf, is equal to the work function, the energy needed for the electron to escape, plus the kinetic energy that it escapes with. We call this energy a maximum kinetic energy because we're assuming that the difference in energy, all of it goes into the electron that escapes, and none of it is dissipated due to sound or heat, etc. We can now use this to find the work function in this specific question here, actually, because how you know you want to use it is it tells you the maximum kinetic energy. So in this case, work function is equal to hf minus kinetic energy. We know that h is Planck's constant, so that's equal to 6.63 multiplied by 10 to the power of minus 34. Multiply onto that the frequency. We actually don't have the frequency, but what we do have is the wavelength. Because it's light that we're talking about, we know it travels at the speed of light, pretty much in the words. We know speed is also equal to frequency times wavelength, so we can rearrange this to find frequency because we have speed and wavelength. So for frequency, we can input in the speed of light divided by the wavelength of light. So that's 0.6 micrometers, but you want to multiply it by 10 to the power minus 6 to turn the micrometers into meters. You then subtract from that the maximum kinetic energy, which is 2 times 10 to the power minus 19. 2 times 10 to the minus 19. You put all of that in a calculation, and because I've done it beforehand, you get a value of 1.3 times 10 to the power minus 19 joules. So that's another way that you can use the work function in calculation. By the way, if it did say find the work function in electron volts, this whole calculation is done in joules, but then just like before, to go from electron volts to joules, you multiply by 1.6 times 10 to the minus 19. You do the opposite to go from joules to electron volts. So you divide all of this by 1.6 times 10 to the minus 19. And if you did, that will get you 0.81 electron volts. Thanks for watching. I hope this video helped. If you have any tutoring inquiries, be sure to visit my website www.excellineducation.co.uk. It's on the first link in the description too.